Okay, so I'm going to talk about something called parameterizing above a multiplicative guarantee. Okay. And this is a joint work with so how a typical parameterized problem look like? So a typical parameterized problem looks like, do I really need this mic? Okay. Is that you are given an input so you're given an input, whatever it could be. So I have input and I have instance, some non-negative integer k, and parameter could be something. For now, let's say k, and then there's a question to be addressed. So this is a typical form of any parameterized algorithm, and we are looking to design an algorithm with running time this, where the dependence on input size is independent of the parameter k which I chose. Okay, so let's look at a very simple example. If my instance was a planar graph and my non-negative integer was k, and my question was, does G has an independent set of size k? Can I answer this question easily? What do we know from the four-color theorem? Four-color theorem tells us that every planar graph G has an independent set of size at least n over 4, right? Because at least one of the color classes will have size at least 1 over 4 of the total size. So clearly, the one trivial algorithm is I check whether k is less than or equal to n by 4, say yes, or right? Because if k is less than or equal to n by 4, I know answer is yes. Otherwise, k is greater than or equal to n over 4, so n is less than or equal to 4k, and I can still try all possible subsets of size k as my potential independent set. So in 2 to the power k time, 2 to the power 4k, I can check whether G has an independent set of size at most k or not, right? Did we do anything at all? Nothing. Like, we just looked at this parameter and checked either it is less or it is more. If it is less, because of the guarantee which is given by the problem is poly time solvable. Else, k is too large compared to the input size, and hence any algorithm which enumerates all possible solution is your parameterized algorithm. So this phenomena is not uncommon to just this problem, but there are other two problems which people studied. Say, for example, max sat or max cut, right? And I ask same question: does there exist an assignment that satisfies at least k clauses? Does G has a partition V1, V2 such that E V1, V2 is at least k, where this means cut edges. Okay? Does for such problem also we have a trivial algorithm the way we have here? Right? If you use probabilistic method or nothing, look for MaxSat, look at an assignment, any arbitrary assignment. Either it satisfies half the clauses or its complement satisfies half the clauses. So I again can say same thing here. Is k less than equal to m by 2 or k greater than equal to m by 2? And if this is this, answer is yes, k is greater than equal to m by 2, m is at most 2k, and you can somehow manage to show that if there are number of variables also somehow bounded, and then like there are only 2k clauses, so because there are unbounded sets, so you can also get that n is bounded by something, and you can try all possible. But there are also algorithms which run in time some 2 power m or something 4, and you can do these things. Same with the max cut, right? If you take a random partition, you can show half the edges are participating into the cut. So again, I can say this, and here, now how do you show that n is less than equal to k? Look at if a graph is connected, it has a spanning tree, right? If it has a spanning tree, it's a bipartite subgraph, right? So k better be greater than equal to n, right? So n is at most k, and then any 2 power n algorithm is also. So basically, all I'm trying to tell you that these kind of parameterizations are not interesting, and in late 90s, and Raman came up with this notion of additive approximation, additive FPT algorithm. So they ask, well, these are obvious questions, obvious answers. We are not making any new algorithm. So for example, for MaxSat, they asked, well, can you satisfy at least m by 2 plus k clauses? For MaxCut, can you satisfy at least m by 2? Can you come up with a cut with at least m by 2 cut edges? Right? For planar independent set, I can come up with n by 4 plus k vertices. Right? So these are much more meaningful questions than what I started with, because still I want to find independent set of size n by 4 plus k. I want to find max cut of size m by 2 plus k. I want to find max set of m by 2 plus k, but the running time which you are allowed to use is this, right? So suppose if I able to do this, and then what does it try to answer? If I ask you, does there exist a cut with size m by 2 plus 10? This gives me a polytime algorithm to test whether the graph has a cut of size half plus 10 vertices, right? So this starts to become much more meaningful question, and these questions have been around for long time, and much more tighter lower bound, upper bound people have studied, and they have tried to come up with an algorithm for this nature. So basically, what is the theme of questions which we are asking here? So this is what I will call it additive parameterization. Right? So what is additive parameterization? So I have some upper bound, I have some lower bound on solution, and the question I ask is, can I come up with a solution which is of size at least this much big, right? Now let's look at, so all these questions are of this nature, except maximum independent set, right? Where even for there it's a lower bound question, but if you notice all these are maximization question. Now let's look at coloring question, chromatic number. We know that testing whether graph G, chi G is 3 or not is NP complete. And we have a trivial upper bound on chromatic number of size n, right? And of course, this upper bound on chromatic number is tight because take clicks of size, like there are infinite family of clicks where each needs n distinct colors to take this, right? So, and because I cannot come up with an algorithm which is f of chi g n to the power big O of 1, think why, because then you will imply unless p equal to np, you cannot have such an algorithm. In fact, you cannot even have an algorithm of nature n to the power f of chi g, right? So it's much more meaningful question that, okay, fine, I cannot do this, but can I save k colors? Can I come up with a coloring which saves k colors? And this is what you heard in the last talk, that not only you can do this faster, but even if there's a list versions of this and that, this problem is FPT, right? So these questions are motivated from these kind of either the hardness difficulty, or we have a trivial lower bound on the solution side as a function of n. Then we ask the question, what is a, like, can we parameterize the question with this upper bound plus k, okay? And what is known about all these questions are, like for MaxSat, like it is FPT. So for example, if you take max R sat, where each clause has size exactly R, then I think you can satisfy 1 minus 1 by 2 to the power R times n clauses. And people ask this is known to be FPT. For max cut, if a graph is connected, you have actually a bound of size m by 2 plus n minus 1 by 4, right? So much more natural question for connected graph is m by 2 plus n minus 4k. Even this people have been able to show FPT, but whether planar independent set is n by 4 plus k, still open. We do not even know whether this is NP hard for k equal to 1 or not. Okay, finding NP, okay? So this was the state of affair which I was trying to tell you, right? So what did I tell you? That like this is a typical form of question, but this typical form of question has absolutely no meaning when we start to have a guarantee in terms of input size, right? Then we look for a better question and ask, can we come up with a parameterized algorithm which is well beyond, which gives me a solution which is better than the guarantees which is provided to me, okay? So I call this kind of parameterization additive parameterization, and they're explicit, right? Look, this m by 2 is an explicit lower bound in terms of m. This is an explicit lower bound. But for some problems, at times, it is not explicit, but there are some implicit lower bounds. Okay, so let me go back to vertex cover. Vertex cover, right? Now, if you have looked at the factor 2 approximation for vertex cover, what does it do? It finds a maximal matching, right, and takes both endpoints. So clearly, any graph G, vertex cover of G, has to be at least maximum matching of G, right? Now, why I call this an implicit parameterization? Because I do not have any concrete lower bound on the vertex cover side in terms of input size. But there is some parameter which is hidden inside the solution that does provide me a lower bound, right? So if a graph has a perfect matching, then vertex cover of G is at least n over 2. Then the classical parameterization again stops making much sense for us. So what will be the most better question to ask? Is vertex cover of G at least max matching plus k, right? Or vertex cover of G is at least LP value of vertex cover of G plus k. And people have studied even these kind of questions and come up with C power k algorithm. Notice what does it tells you? What do you mean by at most?
Question and vertex cover is at most.
All right, sorry. Yeah, you're right. And people have been able to come up with a design algorithm with running time c power k even for this. So what does it imply? Imagine yourself, I give you a graph with a perfect matching, and I ask you, is there a vertex cover of size n by 2 plus log n? You're still getting a polynomial time algorithm. Because if I have n to the power 2 algorithm, c power k dot n square, you substitute k equal to log n, whatever this constant is, this is like some polynomial. So in polynomial time, you are able to test things. So like this is what I mean by implicit parameterization. And the topic of today's lecture is a slightly different problem called long path and long cycle. So what is long path and long cycle? So these are the two problems which we'll study. Right? Input is g comma k, okay? Parameter will keep changing, but for now, let's say k. And question is, does g has a path of length at least k, okay? And if I ask cycle, then becomes cycle of length at least k, okay? What is known in literature, or what was known for a long time, is that if you're looking for path of length k, cycle of length k, not at least, then you have c power k algorithm. The best known currently is like for deterministic randomize is 1.66 to the power k, and deterministic is like 2.6 to the power k. Okay? But if I ask you that does there exist a cycle of length at least k, question completely changes, because a graph next cycle length could be just Hamiltonian cycle for all that you care. But all I'm asking, if there exists a cycle of length at least k, please output me one. But maybe there is no cycle of length up to 100k, but there is a cycle of length 100k plus 1, for example. Right? So this is slightly different question than just asking, does there exist a cycle of length k, for which color coding applies. But for this at least k question with respect to cycle, I mean, you can reduce to one of these problems, but it's a good puzzle to try. Okay? But anyway, so even for this problem, which we need an algorithm, even for at least, we can get it something like 5 power k algorithm. Okay? Like it's even better than this, but for now let's put it 5 power k. So what is so if I give you two vertex s and t in a graph, what is the natural lower bound of path between s and t? Like any path between s and t should be of length at least how much? Shortest path, right? So dst definitely gives a lower bound on the path length which I'm looking for. So the natural question could be, hey, is there a path between s and t? Path between s and t of length at least dst plus k, right? Shortest path plus k. And people studied this problem in 2008, 17 or 18, and they came up with an algorithm with running time some c power k for this problem. So notice, this is also an implicit parameterization. The shortest path between two vertices s and t, it's a dependent on the graph. There is no fixed this thing. So now let me ask another question, which is what we'll get to, and we'll try to see some algorithms for this. Simple ones. Okay? So similarly, if I ask myself about long cycle, what is the lower bound on any cycle length for a graph? Girth, like shortest cycle of this graph. So one natural question I can ask, does there exist cycle of length at least, and this is length of the shortest cycle. Okay, so let's try to make an algorithm for this problem. Okay, so what are we looking for? So we want an algorithm, and you know that girth of a graph can be found in polynomial time. You can find shortest cycle in the length of the shortest cycle. I just check, is girth of the graph less than equal to, say, 2k plus 6? If yes, what can I say? Then I'm looking for a cycle of length at least some 3k plus 6, right? And I can run one of these algorithms. In this case, if my girth of the graph is a function of k, then the cycle length which we are looking for at least is also some function of k, and I can run my normal classical FPT algorithm. But the problem is when girth is large compared to the k which we are trying to talk about. Okay. Okay. So now let's look at a graph. So what is the case we are in? Girth of the graph is, say, 2k plus 6. And now let's look at our solution. So solution is some cycle. Okay? Pick up a vertex u, any vertex u, which I don't know. For now, suppose I pick up vertex u, v, w, x. Okay? u, v, say let's call this number g. So u, I start from u, I traverse towards v, and v is g by 2 minus 1th vertex. Okay? What is w? Another g by 2 minus 1 vertex. Starting from v, w is another g by 2 minus 1 vertex. Because look, this is a cycle of length at least girth of g plus k, where girth is large enough. So I can. And what is x? So x I'm going to take at additional distance, say k prime equal to g plus k, okay, minus 2 times 2 minus 1. Right? So I just sum them up and I subtract from g plus k, this distance. So now tell me, what is k prime? K prime is element of either k plus 2 or k plus 3, depending on the ceiling. Right? Either this is k plus 2 or at least k plus 3. Okay. First question to ask ourselves. Whatever this path is, uv, my claim is, first claim is, u and v has unique shortest path. Okay, unique shortest path. Suppose not. Then there is a path from u to v, right? So I take shortest path from u to v, right? Either it can intersect this portion or it may not intersect. If it doesn't intersect, what is the cycle length of this? Is strictly less than g. That's not possible. Girth of the graph is much bigger. Okay, fine. So it intersects. If it intersects, I get even a shorter cycle. So what did we learn? Learn that u and v is actually the shortest path, and it's a unique shortest path, and this is here. I can argue same with v and w here. I can also argue w and x exactly here. So if I look at this cycle, it has a property that there are 3 vertices u and v and w and x, such that from u to v there's a unique shortest path, take that. V to w there's a unique shortest path, take that. W to X, there's a unique shortest path, take that. And after, since they were unique shortest path, you try all UV, W, X as a potential cycle, delete them up, all these paths, and then check, is X reachable from U? If it is reachable, then you have got your cycle of length more than this, and you are done, right? So, I mean, I may not have been completely formal but formal enough. So this is where our question actually came in. So fine. So Gj plus K is not, I mean, yes, we can do this, it's interesting, but what about asking the following question? Okay. Does there exist a cycle of length at least K times G of J? So up until now, we have always been talking about something parameterization which were additive. And this is why the title of the paper comes above a multiplicative guarantee. Okay? So now only I have reached to the question, is that I am interested in, does there exist a cycle of length at least K times the girth of the graph? Okay? Answer is very, relatively very simple. And I'll show you an algorithm for this in a minute, which is easier than this algorithm. Okay? It's just that one has to know right tools at the right point of time. Okay. It's a fun thing. So we'll do some Pigeonhole Principle. Okay? So let me draw a wheel. Okay, let's give them some name. This will finish my proof, don't worry. Okay, how many vertex disjoint cycles do you see? Let's first draw them. So let's start from A1, A2. This is one vertex disjoint cycle. This is another vertex disjoint cycle. This is another vertex disjoint cycle. This is another vertex disjoint cycle. And this is another vertex. I cannot take these things for now. So let's for now just rub this. I mean, it wouldn't matter much, but let's just rub this. So if my parameter was, suppose my graph, I can find such a structure in my graph. Suppose I can find like exactly like this. So these are cycles. What can we say about these cycles? All length of each of these cycle has length how much? At least girth. Okay. So if I had it's at least girth. Okay. So there is each of these guys has at least girth. Okay. But how many total number of edges are there in these cycles? As many as vertex disjoint cycles. So 5 times. So suppose for now K equal to 5. Right? I definitely got 5 times G of G. Okay. Now let me draw 2 more cycles to you. Okay. Okay. So here's my one cycle. This is bad colored, so let me use. Okay. So you will see. This is one cycle. This blue color, whatever I have drawn, is a cycle. Okay, let me draw another cycle for you. Okay, so it took this. Okay, so fine, let me take this. Yeah. So look, this cycle is covering all the edges of those disjoint cycles which I left. Yeah, this is okay. So I have traced two cycles. Okay, two cycles. What is the length of this curly cycles and the blue cycles? Length of this curly cycle and blue cycle definitely is at least 5 times girth of G. Why? Because look, it definitely covers all the disjoint cycles. Like they overlap in each other, but together, if I just sum them up, the length of the cycle plus this with their intersection and everything, they're definitely more than 5 times GG, because they not only intersects, they definitely cover all the edges of the disjoint cycle. This is how I made my cycle. So this is true. So by Pigeonhole principle, either this is at least half times this or this is at least half times this. Right? So if I would have started with such a structure which had at least 2k vertex disjoint cycle, then what can I say? Either this is at least k times G, or this is at least k times girth of G, and we are done. Right? So what was the strategy? Strategy 1, I first got lot of vertex disjoint cycle that gave me a lower bound on the total length. And now, because of this wheel-like structure, I gave you 2 ways to form cycles which covers all the edges of this disjoint cycles, which gave me a lower bound on totality of these 2 cycles based on this disjoint thing, and then I applied this. Okay? Well, so that ends my proof that if I can find such a structure, I am definitely done. And the great thing is, such objects always exist in a graph. So if as a topological minor, so this, let me use a big hammer from, I mean, it's not big hammer, one can prove using simple things. So what does this theorem tells us? So this is a classical theorems from graph algorithms. It tells us, so this is a theorem. This is what we needed. For any k natural number, okay, any graph G of tree width at least 60 times k square contains a k prism as a topological minor. Okay. So what is the meaning of this? It basically means that I will be able to get such an object as a subgraph. Right? Such an object as a subgraph in the following sense. So there will be a mapping. So what is a prism? This is what is called k prism. If you have like this, and if you have k such sticks, then this particular structure is called k prism. Okay, and what is the meaning of as a topological minor? So I will take this k prism. For every vertex, I will have a mapping, and for every edge, I will have a vertex disjoint mapping. So I will map every edge from here to a path in my graph. And what is the property of these paths? They are mutually vertex disjoint. So basically, I have these structures as exactly what I explained, but these lengths may not be the same, like for these things. But it is at least a cycle, and hence its length is at least girth. But this could be a path in my graph. So all this tells us that if my tree width of graph is larger than this number, then I can find such a big object. And if I can find such a big object, then I know my instance is an yes instance, because from this I can derive a big length cycle. So now my problem has just two things to do, right? I just check. So given an input G, what do? First of all, I make sure that the girth is large, because this is what we use to say that K, like this K prime is of this large, otherwise I would not have been saying. So what is the question? So if the girth is this, check using known algorithm. Otherwise, G, tree width of G is less than equal to 90 times K square, or tree width of G is more than 90 times K square. If this is, answer is yes, here's the proof. Right? This can be found in polynomial time, and given that there's polynomial time, we can come up with this cycle and we can output the one with the maximum length. Okay? And if the tree width is less than equal to 90K square, oh, this is like tree, and on trees, Hamiltonian cycle or longest cycle can be found in time, C power tree width. So this will become C power some 90K square, and we are done. Okay? So we are done. So now, at least I have given you one non-trivial algorithm for multiplicative guarantee. I still have time, so let me give you for vertex cover. And let me show you that for feedback vertex set, we cannot have such algorithms. Vertex cover is slightly easier. Yeah, I have 9 minutes. This should be enough. Okay? Okay. So what are we interested in? So here is a lower bound on vertex cover of a graph, right? So if vertex cover must be girth by 2, because you have a matching, right? So suppose if I'm interested in this question and I want to derive such kind of algorithm, okay? So I know a very classical theorem from graph theory, which is called Erdos-Posa theorem. What does Erdos-Posa theorem says? Either says for any integer k, either G has k vertex disjoint cycles, or FVS of size alpha times k log k. So that is like order k log k. Okay. So let's apply this lemma with k prime being equal to 2k plus 1. What will happen? Either it will give me 2k plus 1 vertex disjoint cycles. Then what can I say? Look, for each of this cycle, I have matching, right? I have matching. If I take alternate edges, I have matching, right? So for each of them, I'm going to spend how much time, like how much vertices from the vertex cover? Gj by 2. You only asked me for vertex cover of size at most, yeah, this is correct. And I'm looking for a vertex cover of size, vertex cover of G of size at most k times G. Now, each guys take Gg by 2. So into 2k plus 1, what does it imply? It gives me a guarantee that vertex cover of this graph is at least this, so I say no. Otherwise, in the second case, I have a feedback vertex set of size order k log k. If I delete it, what I get is tree. So this has a tree width. In the other direction, tree width is like order k log k. Now there is just 2 power tree width algorithm for vertex cover. So 2 to the power big O of k log k over log. Okay, I could also have asked the same question about connected vertex cover, because vertex cover forms a lower bound. This case will be anyway no, and the other side anyway I have a graphs of bounded tree with, I can do anything I like. But what about feedback vertex set? Makes sense, makes a lot of sense to ask, what about k times feedback vertex set? The problem with feedback vertex set is you subdivide them enough number of times and take a big small cycle outside, and now nothing. Like, the problem is girth does not gives you a good lower bound on feedback vertex set. Girth only tells you that if you have a girth, then the feedback vertex set size is at least 1. So it doesn't provide you a lower bound. So you can use this idea to come up with a reduction. And I think that's all that I wanted to tell you. Thank you.